Welcome to Young Tuition. Today I'm going to discuss some basic issues on electricity. In particular, this talk is in response to some recent claims by two popular YouTubers. If you haven't seen these two videos by the Science Asylum in 2019 and another by Veritasium very recently, then please go there, have a look, and then come back to see my response. First, I must point out, both of them proposed that the electrical energy stored in the battery can be transformed, not through the wire, but through the electromagnetic field. And their basis is the definition of Poynting vector. We're talking about Poynting vector later, but this S represents that particular vector. Why did they choose Poynting vector to back their claim? Because in the context of studying electromagnetic wave, Poynting vector provide not only the direction of electromagnetic wave, but also exactly the energy flux of electromagnetic wave toward that direction. Okay. But my first remark is that this diagram around the battery is incorrect. Now, the red color represents the electrical field. The blue color, the loop, represent magnetic field. Now, this is based on two assumptions. First, the positive charge is accumulated on the positive side permanently. Negative charge is accumulated at the cathode permanently. And therefore, according to electrodipole field, then that's how they draw this the diagram. But because that electric field is static, therefore, it is impossible to find magnetic field if the power switch is open. The second assumption is that when you switch on the switch and the current will move along the circuit. In the meantime, that is their second assumption, that the current will go through from the negative to the positive. So because the current moving upward, therefore, according to the right-hand row, the blue color, the direction or distribution of static magnetic field can be worked out. That's true. And if these two hypotheses are correct, and indeed the yellow arrow will represent the direction of Poynting vectors, radiant toward direction. But I would like to draw your attention to this fact that in the battery, that there's only the electric field is static, because battery during the charging process, the potential difference between the two terminals eventually diminish. Therefore, the electric field gradually, the strength of electric field strength gradually decrease. However, there's no charge. There's no current moving between these two terminals. So therefore, because according to Maxwell equation, the current density, the current vector is zero, and also the electric field is time independent. The magnetic field around it must be zero too. So this is my first response. Secondly, if I look for, if this is a very colorful diagram, very complicated, but if I simplify this diagram, you will see the argument is based on this assumption. that this is positive, this battery is positive. We know that electrical current go from positive to negative. For the electron, because it's negatively charged, so the electron actually move backward to the positive side. Now, the argument was made that if the electron actually leaving this area, so therefore there must be some net positive charge. And because the metal and those positive charge will distribute evenly on the surface. That is how they explain that. That is the assumption they made. So therefore, can you see this positive sign represent the positive charge on the surface of the wire, presumably the copper wire. So therefore, that's why if you just pick up one of the electrical field, indeed, it radiates on both sides. In this case, you can use the right-hand rule to work out the direction of Poynting vector. Indeed, it is moved along the wire. Of course, this assumption is not very reasonable, okay? And especially if you go to the other side. By way of contrast, they assume that the surface, the other loop, other half of loop, the surface is full of the negative charge, presumably is negatively charged particle must be electron. How can the electron move on the surface in the other half? Well, anyway, according to this assumption that you can see the electrical field will be moving into the wire from all directions. Therefore, again, you can work out that the direction of the Poynting vector is still go along the surface toward the electrical bulb. By the way, these two YouTubers have different assumptions. If I go to this one, you can see now in the Science Asylum, the situation is slightly different. And in this case, they argue that there is a non-zero electrical field upward in order, because the fact that is because you say electron is moving, well, this could be the positive charge, the particle, because electron should go backward. So that is why it was assumed that the electric field near the surface of the wire is the parallel to the surface. And hence that not this is energy flow, but hence the Poynting vector is toward the surface. And some people even argue that, well, this would be the same for the load and a wire, because that is also explained that this direction of Poynting vector was also interpreted as that energy is actually moving from the space into the metal wire. Just return to this diagram. So this is inconsistent. See, how can you? This is something I think people would like to ask. How come that in the upper half of loop, the surface is full of positive charge particle? And how about in the second half, and this surface is full of negative charge particle? So that is remain unexplained. Okay, there is some inconsistency. In this case, you can see that apart from the positively charged distribute evenly around the surface, and there are also additional electrical field. Can you see electrical field here? And toward the direction opposite of the direction of the moving electron, because that the direction of the electric field is the direction of how the positive charge is accelerated in the electric field. And this is, but care must be taken seriously. And in the first place, if this part represents the conductor, a good conductor, copper is not bad, and then we would expect that the electric field should be very small. Why? Because a good conductor, the electrical potential difference at two ends must be very small, because the resistance or resistivity is very small. So you can argue that the force acting on that particular electron in this case can be represented by this one. So because for a good conductor, these two potentials at both ends are approximately the same. So we would expect that the electrical field should be very close to zero, not as strong as that. This is especially true if the motion of electron in the superconductor is not caused by electrostatic force, electrical field. So that is another comment here. Let's go to the this most important part. So the important question, how does the assumed electrical power move into or absorbed or transformed into the, in this case, to turn on the light bulb? There's no explanation. There's no explanation. They just assume that energy, just like a fluid, can move. So basically, this diagram simply shows you that the electrical power or energy can move, can flow, okay, guided by the electrical wire, conductor wire, and eventually it ends up with the space where the electrical bulb is located, or any electrical appliance. You mentioned the washing machine, the microwave, or refrigerators. But how can this energy hang on the space can be absorbed, magically transformed into that particular resistor? They didn't explain. Now, let's just go to this diagram I used. So this is my diagram to redraw that what's going on at the electrical bulb in this case. So what happens is that electron inside that resistor, equivalent resistor of electrical bulb, is actually accelerated by the electrical field. This force, Fe, is actually determined by the product of the Q and the electrical field strength. And by the way, if these wires are good conductor, the potential difference between these two terminals of resistor should be very close to the voltage of the battery. So in this way, we can work out the power. The power will be determined by the current and the voltage difference. So that is how traditionally how we explain that the electrical power consumed by a particular electrical appliance. But in this diagram, another thing I have to explain that in this case, you can see the current, because the current is actually moving downward. Using the right-hand row, we can find the distribution of the magnetic field around that particular resistor. However, it must be make it clear that this static magnetic field is generated by the moving electron inside the resistor. This magnetic field has nothing to do with the magnetic field possibly exist around the power supply, as I first noticed. Of course, if you use the right-hand row, you still can argue that the direction of Poynting vector is actually into the resistor. But care must be taken. This diagram only shown that the cross product of the static electric field and the static magnetic field is toward the resistor. This doesn't imply that there must be a certain amount of energy flux moving into resistor from space. It's completely, this is a very basic idea in physics, right? You cannot imagine that something static, and just because that the E cross product B will give that direction, not necessarily mean that the engine can move into these particular physical devices. If so, tell me, how can we interpret, how can we describe the absorption, emission, re-emission, and transmission? Do we treat this Poynting vector, this is a magical energy flow as type of the radiation? You can't. It's terribly wrong. It's terribly wrong. But this is some remark I have to make sure to convey that the static magnetic field near the bulb is generated by the moving electron inside the bulb rather than from the remote power supply, as I had just explained. Second, the net electrostatic force F, that's the very interesting part, small f, on an electron near the bulb originated from the repulsive Coulomb forces among electrons themselves in the wire, irrespective of whether the residue electrical field is zero or not. What does that mean? If you go to the diagram here, you can enlarge this one, you can see that. Because of the local electron near the resistor or inside the resistor are constantly forced to move upward. You can see the density of electron in the upper end will increase. Hence, the inter-electron distance will decrease. So therefore, inevitably, because of the repulsive nature of interaction among electrons, so electron will be pushed by this repulsive force toward the anode, to the positive side. On the other hand, because there's a shortage of electron on the bottom, inevitably, electron on the way to that resistor will be pushed by the electron behind it. As a result, electron will move as we expected in the DC circuit, not by any statical electrical field, but by the repulsive Coulomb force of electron. Of course, this phenomenon can also be interpreted as a diffusion. See, simply because the density is crowded, more crowded, so therefore they want to get equal distance. So therefore, that is the formation of current in the conductor wire. That's my point. So electron will move along the opposite direction of the electrical current, just by convention, but the driving force, the driver, has nothing to do with electrostatic force as determined by, used by this potential difference. Okay, not by potential difference. Okay, in other words, electron can move accordingly from negative to a positive side in the absence of the potential difference in the conductor wire. Okay, that's very important because ultimately, according to Ohm's law, at a steady state, these two currents must be the same. Of course, you can imagine that at the very beginning, when you suddenly to switch on the switch, it is unlikely that the state can be achieved instantaneously. Okay, any other thing? This is my hypothesis. I must make it clear that because you see the answer to the question in the video is open to many secondary hypotheses. For example, how to treat that nearly parallel conductor wires. So many electrical engineering people would just spontaneously use, this some kind of equivalent circuit. They use. I noticed one of them actually published the computer simulation based on using the equivalent capacitors and the resistors, and to both ends. Eventually, they can assume they got some preliminary result in the nanosecond scale. I'm surprised. That I think is very good. However, we have to be careful when interpreting this result. I'm talking about the main part of my theory now. That this diagram, and it's just complete this diagram this afternoon, and you can see I just alter that original question slightly. I assume that a half of this conductor wire is using the superconductor. So therefore, we don't have to consider that the resistance of the half of that conductor at all. But on the other hand, we need to consider resistance, although it's very small. For example, for the copper wire, the resistivity of the copper wire is relatively small, or much smaller than resistance of the bulb. So this is my hypothesis. So there's at the beginning, so this green colored curve represent, oh, by the way, the vertical axis represents the electric field potential, or electrical potential for short. And that's the potential of the positive anode. This is the potential of a cathode. You can see at the beginning, when this switch is off, we will see that potential in this circuit is the same everywhere. That is represented by this green curve. Once we switch on, then some transient stage can be monitored if you go to a very small time scale, especially below the micro or even nanosecond. You should be able to see many unstable transient response, depending on the model you use. Oh, by the way, in physics, we don't study real object. I forgot to tell you that. So this question is open always. And because the answer is very dependent on how do you apply your model, how to define your model. So therefore the answer could be different. However, my response is focused on whether electrical power can be transported by static electromagnetic field. Okay, of course, basically my answer is negative. Okay, but can we just return to the diagram? So these colors, the purple one, will represent such one of the transient potential distribution along the second half of circuit. And this time scale is determined by the light speed. We have no alternative but assume that the electrical field in the conductor can influence other at the speed of the light. But who knows? It could be even faster. Anyone can measure, actually turn on and to measure how fast that is. Does that really, I mean, not a simulation, but a measurement. Okay, it will be interesting to know how fast and the static electrical field can influence the remote charge or remote potential. In this case, particular case, the potential. So I did this exactly at this time. And of course, this is ideal case. Air is half of this loop. So if this condition satisfy, my assumption, my hypothesis is that the perfect the potential were established. But at this stage, the current may not detectable. So I approximate that at this stage, at stage 1, stage 2, only when they achieve the second stage, but still the current in the conductor are still beyond detection. Well, namely 0. Why? Because that we have to accept that you enable all electrons in the wire to move. It takes time. However, for those electrons or local electrons in the remote device, and because of the potential difference, it has been established. So instantaneously, the electron will move from negative to the positive. Okay. So therefore, I suspect that there might be some transient stage where the current of the bulb or the light is on, before we can measure any the current in the conductor. Well, this is a hypothesis. Okay, if you have any equipment facilities and do something. Okay, but eventually, as I just explained to that, because of this density change, because of this density change, let's return to my diagram here. That's my simple. This is my simple model in Z. So once the potential difference is established at speed of light, not directly, not a jump from battery to the bulb. In my opinion, that is unlikely, very unlikely, almost impossible. Because of this, the local electron are forced to move. Therefore, the current is formed inside the bulb prior to the current in the wire connected to the bulb and supply can be detected. The answer to this question is not unique because the question itself is not well defined. But I must emphasize that the idea that a statical field, statical electromagnetic field can transport electrical energy is untrue, is physically untrue. Okay. Let's jump to the final diagram. I thought I will mention that earlier. This is my final diagram. So in this diagram, I just challenge those who believe that just because the product of the statical electrical field and the magnetic field will give a direction, which in the context of electrical wave, which must be the direction of electrical wave and also is the direction of energy flux, doesn't necessarily mean that you can actually realize the energy transfer technology. So from this diagram, you can see that we can simply build that uniform electrical field by use a capacitor. And then if you just use some permanent magnet, if you just use some permanent magnet like this, okay, costs nothing, and make to build the uniform magnetic field perpendicular to that electric field. Indeed, you can create a direction which is parallel to the vector product. But can you actually use this force to this energy to achieve the energy transport? Think about it. This is an essential difference between electromagnetic wave and the model the two YouTubers had been proposed. Namely that when we describe electromagnetic wave, I have acknowledged that one of the YouTubers, I used part of his diagram. Anyway, so basically, electrical field and magnetic field are perpendicular. In addition, both electrical field and the magnetic field are oscillating at the same frequency, same amplitude, and same phase. Do you think the diagram the two YouTubers used can satisfy this condition, the basic time-dependent field condition? Of course not. My suggestion is that it's misleading to borrow this Poynting vector out of the context of electromagnetic wave and trying to dig out some new implication. I will end my talk by showing this cartoon again in the context of the electromagnetic wave and the context of static electricity. And we cannot simply trust mathematics. Okay. I will stop here. Thank you for watching and looking forward to your comment and critiques.